All right, so any questions?
It's about as fast.
Yeah.
But I'm more, it's linked. Do you think actually could have thought of like a theorem on how to solve the general proof of like the
Fermat?
yeah, Fermat?
Do I think he actually had a proof?
Yeah.
Most people think no. I don't think so either.
Was it just too complex for him to do it on his own?
If he had a proof, it was totally different from everything that people have been doing for the past 100-some years.
Maybe a simple one still exists?
Yeah, it's possible. So there's two possibilities. One, there's a really clever, simple way to think about this that most people are just missing. Or two, he simply made a mistake, right? He thought he had a proof, but if he had actually written it out and looked at it, he would have found some sort of oversight. Because initially, lots of people came up with proofs, and they fell apart very quickly. And then later, the proofs became harder to find errors in, but they all seemed to have errors until 1991 or 2, I believe. Yeah?
I have a question for the PhD.
Mm-hmm.
I don't think I can list like two different array for the first day.
Wait, say again?
I mean, for the can I use array or like
Got to use linked lists.
link list?
Yeah, only linked lists.
Okay.
Yeah. If you want to write a version with arrays, that's good practice. But it's got to have linked lists working. No, seriously, because that'll be you're supposed to know how to do it with arrays also.
Yeah.
So. But yeah, for PA3, it's got to be linked list based. So there was a typo in one of the ODPs. When I prototyped the function, I had the star on the wrong side, and somebody pointed that out to me. So I fixed that on the README, if that was throwing you off. Right, so the prototype should be struct tnode star small instead of struct star tnode, which is a syntax error. So any problems with this ODP other than the typo? All right, and I'll probably post another for tomorrow morning. Yeah. So, and also I posted a note, /temp/PA3 sample is a sample version of PA3. You can run that to see what it should do. And I got rid of my memory leak, so you can even val grind it. Yay. All right, so if you have doubts what the program's supposed to do and what its output should look like, you can go to that, or you can ask. Other questions? All right, let's talk about the midterm so that we don't have to worry about it. So I posted a sort of study guide. So possible topics for the 222 midterm. I might be missing something here, but this is certainly the major highlights. But also, anything that you did in 224, you should be able to do If I asked you to do some input, you should be able to do an fgets or process command line arguments or things like that. But the mainly new stuff from this course, so structures, right? Definitely know how to use the structure statement. You've been doing that since week 1. I think everybody's good with that. How you define a structure, how you make a pointer to a structure, how you allocate memory for a structure, so that's a malloc statement, usually size of, struct whatever the name of the structure is, how you access the fields of a structure. If it's actually a structure, you can use a period to access a field. If it's a pointer to a structure, you would typically do something like star variable to get to the actual structure, and then say dot field. But we don't do that. We just say variable arrow field. And that means this. It means take the thing pointed to by the variable and then pull off the field of that structure. And arrays of structures, I don't think we've really done arrays of structures yet, but it's like regular arrays, right? So you can say structure node variable bracket 100, and you've got an array of 100 struct nodes. So I don't know why I put that on there, because we don't do structures in arrays much. Linked lists, you definitely want to know all about linked lists. So sentinel nodes, searching a list, traversing a list, right, going through from beginning to end, inserting and deleting. Okay, the concept of a doubly linked list, so you simply have forward and backward pointers. Order of complexity of list operations and array operations and how those compare. Right, this was our motivation for doing linked lists versus arrays. So an array, if it's unsorted, so insert, delete, search. An unsorted array we can insert in a single operation, just tack something onto the end. We can delete in possibly a single operation if we have something like a valid flag, which says this thing is no longer a piece of our array. We could just set that flag to 0. So that could be order 1. Or if we want to actually squeeze everything up to overwrite the deleted element, that could be order n. And searching an unsorted array is definitely order n. If you have n things in your array, you'd have to take n operations to look for something in that array. If it's sorted, then your insert becomes expensive. Because to insert anywhere except at the end, you need to move things down to make space. And so that becomes order n. And to delete, that's generally going to be order n also. But to search is now just log n. We can do high-low. A linked list, which we're assuming is sorted. If it's unsorted, it's the same as an array. But a sorted linked list, we can insert with a single operation. We can delete with a single operation. But it takes n operations to find something in that array. And so to insert something to keep the list sorted, it takes one operation to actually do the insert, but it takes n operations to actually find where you want to do the insertion or the deletion. And this is not on the test, but when we do a binary tree, our insert will go up to log n, our deletion will go up to log n, but our search will come down to log n. And so overall, this is going to get us better performance. But no trees on the test. All right, so that's what I mean by order of complexity and by lists versus arrays. Star and ampersand, right? Star variable is a thing pointed to by that variable. Ampersand variable is the address of that variable. Okay, they go together, and that arrow symbol is saying pull off a field from the thing pointed to by a variable. So it's that shortcut. You should know the concepts of pass by value versus pass by reference. Pass by value means you're simply sending a function the value of some variable. Passed by reference says you're actually giving it the location of that variable. So C, when you call a function and you pass something to that function as an argument, you're always passing the value of it. But if that value represents the address of a variable, then technically we're passing that variable by reference. But the address we're passing is still being passed by value. So we've talked about that before. Malloc and free. Malloc is used to allocate space. Free is used to release something that you previously malloced. You can only pass free something that you got from malloc. You can't just free an arbitrary location or it will complain. And valgrind is our favorite friend who tells us if we're freeing everything that we're mallocing, and also tells us if we're doing legal or illegal things when we malloc. So if we try to malloc something but it's not the right size, or we try to use something that's a different size from what we malloced, valgrind will let us know about that. Okay, GDB, your friend for debugging. So you should know how to compile with GDB. That's a -G switch. You should know how to start GDB. So GDB executable name, and then you can say set break and put in breakpoints. You can say set watch to set watch points. You say start to kick the whole process off, and you can either say next to step to the next line of code. You can say step to step into functions if you're about to call a function, and you can say continue, which just says run until you get to a breakpoint, an error, you exit. And you can print variables, you can examine memory with the P and X command. And that's pretty much what we've been doing with GDB. Okay, so be comfortable with that. Make files, you should know the basic concepts of a make file. Again, I'm not going to make 50% of the test on make files, right? Because that's really a 224 concept. But I may have something in there on, there may be a make file question, maybe a short answer or something like that. Because I want to make sure that you're still comfortable with these things that we're going to be using in 222. Abstract data types, this is a concept, right? So there's a difference between a stack, which we think of as a linked list, or a stack that we think of as an array with a stack pointer, versus a stack which we just think of as something which acts in a first in, last out fashion. Something which we can push stuff into, and when we say pop, we get the last thing that we pushed. Okay, that's the abstract view of a stack. It has nothing to do with how it's actually implemented. If you're thinking push means go to the sentinel, create a new node, have the sentinel point to it, you're not thinking of an abstract stack. You're thinking of a particular version of a stack, a particular implementation. As an abstract data type, a stack is just this thing that holds data. We put data into it by saying push. We pull data out by saying pop. And pop pulls things out in the reverse order in which they were pushed. Okay. Stacks. So basic operations on a stack are push and pop, right? Plus maybe initialize. If you try to push too many things into a stack, you can get an overflow. If you try to pop too many things from a stack, you get an underflow. And two ways to implement, with arrays and with lists. Okay, PA3, you're doing implementations with lists, but make sure you know how to implement a stack with an array. This will probably be one of your questions on the midterm, because I want you to know both of those. Same thing with queues. You can insert, make sure you have the order of insertion and removal correct. So you insert at the tail, you remove from the head. Okay, think of the head of the line, think of the back of the line, or the tail of the line. You're supposed to start at the back of the line. You get in trouble if you cut into the front of the line, the head, right? So insert at the tail, remove from the head. And so you're removing in the same order that you were inserting. If your queue is full, you can't put anything more in it. If it's empty, you can't remove anything from it. And two ways to implement, with lists and with a circular array. I promise you I will not ask you on the midterm to do anything related to circular array implementation of queues. Okay, but I might on the final. So play with those sometime between now and then. But the idea of an array where you have a head pointer and a tail pointer, and when you get to the end of the array, you wrap around to the beginning and so on. And that's quirkier than a stack. So I'll hold you responsible for stacks with arrays, not necessarily queues on the final, definitely not on the midterm. And that's pretty much it for subjects we've gone over, right? So things you can expect to possibly do on the midterm. So writing some code to manipulate a structure, to work with pointers, to dereference pointers, and so on. Okay, lines of code, analyzing code to figure out what it does, or taking a set of code and modifying its behavior, adding something or changing something. Thinking about performance of algorithms, basically, you know, insert, delete, and search on arrays and lists. Understanding list stacks and queues, being able to perform these operations and show what's happening in a list stack or queue, right? And conceptual questions about GDB, Valgrind, Makefiles, and other tools. Does that make sense? So nothing we haven't talked about, mostly stuff you've been doing or working with. Yes?
How many questions?
I think I got 6, but some of them, like the short answer ones, will have multiple parts to them. So I'm shooting for 50 minutes, right? I don't want to keep you here like all day. I don't. Yeah, I might have some multiple choice. I haven't finished it yet, but I've got some of the stuff sketched out. But it's not going to be like 50 multiple choice questions, right? It might just be like 1 or 2. ODP or the programming assignments. Yeah, but I'm not going to ask you to write something like PA1 or PA2, right? So not like that, but the concepts used in there, right, are fair game. But I could ask you to write some piece of that, right? So I think it's 4 pages of double-sided notes or 8 pages of single-sided. Does anybody remember from Canvas?
It's 4 pages of double-sided.
Okay, and 8 single-sided. That's more than you will need, okay? And the code that you've written will not get you points on the exam, okay? So you're gonna have to come up with new code, basically.
So just want to make sure, so just in terms of cover only like P1 to 3?
Nothing on trees,
Yeah.
right? Yep. No trees, no recursion.
So before 2, I mean until like 211, only P211. These things will be in the.
Yeah, now I could throw a structure at you that you haven't worked with, right? And 211 you can do without knowing anything about trees, right? But yeah, basically the stuff before 211.
And when is this?
Monday. Yeah. Is that not the day you wanted to hear?
Well, it's a Monday.
It is a Monday. We got Valentine's Day in there. I didn't want to do a midterm on Valentine's Day. That just seemed kind of rude. And I can't do it Friday because then I got PAs coming in, and yeah. So it's a Monday exam. All right, so that's posted. No surprises that I can anticipate on the midterm. But any questions about any of that? Sure.
So for the ODP for 211,
Mm-hmm.
I got sample and I just compared it to my friend and the code was totally same, but the file was older.
What order?
Like only difference is only the order of the code.
It's like we both, like Alex altered our notes at the very beginning.
Mm-hmm.
It was just like his order of assigning all the values of the notes was a little bit behind.
Which shouldn't make a difference. Is the order of your fields in the structure definition the same? So data and then left and then right? Because that will definitely cause problems. So yeah, make sure the fields are in the same order. But in general, malloking in a different order, assigning in a different order won't make a difference unless, for example, you're trying to use a field in something that you haven't mallocked yet, right? So your mallocs have to come before whenever you use that structure. So that could be an issue. All right, so let's talk about trees as an abstract data type. So we're generally going to implement trees with this struct node that has 3 fields, a data on the left and a right. And we'll point it to null when it's at a leaf node. And an empty tree will be represented by null and so on. But that's an implementation. We could have a different implementation. We could have a tree that has a sentinel node. We can implement a tree using an array, just like we implemented a list in PA1 using an array. We can implement a binary tree just using an array of integers. And we treat each node as a triple of locations in our array. Element 0 is the root data. Element 1 is the index of the left child. Element 2 is the index of the right child. And then element 3 could be used for the data of whatever our first node is that we create after the root. And 4 and 5 would point to the left and right indices and so on. You can do that, right? You don't need to use any pointers. You don't need to use any malloc. We can do this with an array. But those are implementations. So let's look at what a tree looks like from an abstract point of view as an abstract data type. So we have some kind of init routine which returns a tree. Could be a struct node star, could be an integer array, could be in Java a totally different type of object, but it returns some kind of tree, okay, whatever that variable type means. So init basically creates an empty tree, no nodes. And then we want to be able to insert. And to insert, we have to specify what tree we're inserting into and some kind of number we want to insert. And that's generally going to return a tree also. Because since we don't have a list with a sentinel node, sometimes the tree is going to actually change value, right? In particular, when it goes from being completely empty to being not empty. It's changing from null to something not null. So insert will want to return a tree, and similarly delete will want to take a tree, a number that we want to delete from the tree, and it'll return a new tree. And maybe before that, we want to do some kind of Boolean search. So we pass a tree and a number we're searching for, and it somehow returns whether it's found that number or not. So in C, Boolean would typically be an int. And maybe we return 1 if it's found and 0 if it's not. So those are basic operations on a tree. We'd also like to do something like traverse the tree. So let me just make a routine called lnr, and we pass it a tree's root, and that does an in-order traversal. And for this, I'm assuming that as it visits each node, it prints out its value. And maybe we might have a post order and a pre-order traversal routine, or we could have a traverse routine that takes a tree and some kind of flag that tells us how we want it traversed. And that's a more general setup, because then we can have breadth first search, and we could have right left node and all kinds of other things. If left node right gives us our data in increasing order, what's your first guess for what a right node left traversal might do? descending order. And that's exactly what it does. All right, other things we might want to do, we might want something like tell us the height of a tree. So remember, the height is the depth of the deepest node, and the depth of a node is the number of edges from the root to that node. So the height of a tree is the maximum number of edges from the root to any leaf, or to any node, but it's going to be a leaf that's deepest. So we might want a height function. And there could be other functions that we could imagine wanting to have, but this is a pretty good collection. In PA4, these will all be functions that you'll definitely want to implement to interact with the trees that you're going to build. But when we talk about balancing trees, we'll expand on this list. So that's a potential view of a tree as an abstract data type. And again, no reference here of how the tree is actually being implemented. So I have my recursion folder. So we're going to try something here. Yeah. So I want to look at this recursion business. So here's a sketch of some code for doing traversal of a tree in order. So if the root of the tree is null, we just return. There's nothing to print. Otherwise, we call traverse recursively on the left subtree, which should traverse the entire left side of the tree. And then we print the data at the root, and then we call traverse recursively on the entire right side of the tree. And the claim that we've been making is that this will traverse the entire tree in this left node right order. So I want to actually try to do this and see what happens. So we're going to pick on a tree, and I'm kind of making this up. So that should be a good binary search tree. Everything to the left of a root is smaller, everything to the right of the root is bigger. And so if we traverse this successfully in left node right, we should get these numbers out in sequential order. So up here, I'm going to record what our output is. And the setup is, this is what root looks like. Root is pointing to the root node of this tree. It's already been built for us. And now we're going to, in our main program, we're going to say traverse root. And I want to see what happens. So this is what the tree looks like. So this is page 1, and this is called from main. So when this function returns, we're done, right? We come back to main, we finish our call to traverse. Hopefully all of our numbers have been printed. So I want to track the recursion. So the first thing that traverse is going to do is look at the root and say, is the root null? And it's not. The root is this node containing 20. Okay, so it checked that, and there was nothing to do, so it did not return. So now it's going to say, let's traverse the left subtree. The left subtree is 10, 5, 12, 11. Okay, if I lose anybody, let me know, because this is going to get deep. So we're calling traverse on the left subtree. So I'm going to make a call to a new copy of traverse. We were called from page 1. And when we called traverse, what we passed to it was this left subtree, which was 10, 5, 12, and 11. So now our whole purpose, the only thing the CPU is trying to do is run traverse on this tree. All right, so it's going to check, is the root equal to null? Well, no, it's not. It's the number 10, so it doesn't return. Now it's going to say, okay, I want to call traverse on the left subtree. And the left subtree is this node containing 5. So it's going to make another call. So we'll start page 3. This is called from page 2. And the tree that we're passing to it is just the tree containing a single node 5. So it will check to see if root is null, and it's not. So it'll say, let's traverse the left subtree. And the left subtree is null. So now we're making another call to traverse. This was called from page 3, and our root is null. So it will say, is the root null? Yes, it is. So it'll return. So we're done with this call to traverse, and we're back to this execution of traverse, which was on this tree. Okay, it was traversing root left. We're done with that. Now it's going to print root arrow data, so it's going to output a 5. So it's done with that. Now it's going to traverse root arrow right. And so it's going to call traverse with a value of null. So we'll start our 5th version of traverse. It's called from 3. Our root is null. It'll say, is the root null? Yes, it is. It'll return. It's going to go back to page 3. And page 3, it called traverse root right, and it's done. This program is finished. This function is now finished. It was called from page 2, so it's going to return to page 2. So page 2, we were traversing root arrow left. Now it's done. So now it's going to print root arrow data. That's a 10. That's done. Now it's going to traverse root arrow right, which is this tree, 12, 11. So let's go into that. So this is page 6. It's called from page 2, and our tree looks like this. You following this? Right, we're just unwinding this recursion, seeing exactly what happens in each spot, and we can start speeding this up a little bit. So is the root null? No. Let's traverse the left subtree. So that's called from page 6, and we're passing it the left subtree, which is 11. So traverse says, is the root null? No. Traverse the left subtree. The left subtree is null. So called from page 12, we're past a root is null. Is the root null? Yes. So it's going to return to page 12. Page 12, we were in the middle of traverse root left. That's finished. Now we print root data. That's 11. And then we traverse the right subtree, which is null. And let me reuse some of these pages. So this is page 14. It's called from page 12. The root's null. We check to see if it's null. Yes, it is. It comes back. And now this call to traverse is finished. And so it's going to return to page 6. We're popping the stack. Okay. Top of the stack is right here. We just finished this call to traverse root left. Now we print the root data, which is a 12. And now we traverse root right, which is null. So this will be page 15, called from page 6 with the right subtree, which is null. If root's null return, it returns to page 6. And now we finish this version of traverse. And we pop the stack. We were called from page 2. So we're back to page 2. What were we doing? We were traversing the right subtree. We're done with that. So we can return to page 1. We pop the stack once more. Where were we? We were traversing the root left. We finished that call to traverse. Okay, this is the version of traverse that was called from our main program. And we finished this call of traverse root arrow left, and what did we print? 5, 10, 11, 12. That's the whole left subtree. And now we print the root data. That's a 20. And now we need to traverse the right subtree. and I'm not going to run through that one. But this is page whatever we're up to, 16, called from page 1, and we pass it root arrow right, so our root looks like this. And it continues. And eventually this will end up printing out 40, 45, 50, and 60. And when we come back all the way, right, when we finish traversing root arrow right, which was all of that stuff, this call to traverse is complete. We return to main, and we've completed this call of traverse root. Okay, that's all the stuff that's happening when we make this one call to traverse. And trying to follow that with GDB or with pictures will be a nightmare. Okay, so this is a case where GDB is not what you want to do to try to follow all of the execution. Okay, to try to find a problem, you're not passing the right variable or something, right? GDB can still help you. But you don't want to go down all these call frames unless you want to. It's fun to do once. Go down all these call frames and sort of see who called who from where and what the value of each variable was. GDB will let you do that. It'll let you go back into previous call frames. And each of these things, the technical term is a call frame. Right? When you call traverse, you get your own copy of the local variables. You have your own set of code that you're executing, your own place that you are in that code, and so on. But while this is happening, this is still happening, right? So that's the trickery of recursion. So you want to try inserting? We got 10 minutes. I think we can do it. So let's, exactly, yeah. But I won't charge you quarters for this. Let's stick with the same tree. So there's the same tree. And this is page 1, and we're called from main. And let's say we're doing an insert. So root equals insert. Root comma, let's add, let's insert 47. That won't be too bad. So we're calling insert, our number is 47, and our root is, right, this node right here, which points to all this other structure. All right. I'm using two-sided call frames, so we're saving a few trees. All right, so what do? We're inside here. We have a struct node star temp. Temp is nothing right now, okay? If root equals null, then temp equals malloc. Well, it doesn't, so we don't do any of that. So we finished with that. If number is bigger than root arrow data, well, number is 47, root arrow data is 20, right? So we want to execute this block of code here. So this is in progress. So we said temp equal to insert root arrow right comma num. So we're making a recursive call to insert. So here's our second call frame. It's called from 1. And we're inserting the same number, 47, but we're passing it root arrow right, which is this smaller tree, which looks like this. So here's the call we're making now. So temp is nothing. If root equals null, that's not true, so we're not going to do that. If number is bigger than root arrow data, 47 is bigger than 40, so we're going to do this. We're going to call insert, and we're going to insert num into the right subtree. So another call frame. And this is going to be much more direct than traversal. So we're called from page 2. We're inserting 47 into the right subtree of this, which is just 50, 45, 60. All right, if root is null, no. If num is bigger than root arrow data, well, num is 47, root arrow data is 50. So we're not going to do this. So we're going to insert onto the left. So we're going to call insert. We're going to insert num on the left subtree of this, which is just a tree containing a 45. So we make another call. This is page 4, called from page 3. Our number is 47. Our tree is just a single node. Okay, if root is null, no. If number is bigger than root arrow data, which it is, 47 is bigger than 45. So now we're going to say insert into root arrow right, the number. So we make one more call. So here's our 5th call frame, called from our 4th. We're inserting 47, and we're inserting on root arrow right, while the right subtree of this tree is null. All right, so now this code starts to execute if root equals null, which it does. So we're going to malloc. This should be an equal. So we're going to malloc. We create enough space to store a node. We set the data equal to our number, which is 47. And the left and right children are null. So temp is itself a tree. It's a tree containing just the node 47. And we say return temp. So the return value from this call to insert is this tree containing a single node 47. Well, we were called from 4, so we return to location 4. That's right here. And we were doing this statement right here. And so temp should be set equal to whatever this insert call returned. Well, remember, insert returned a node containing a 47, so temp is equal to this node 47. And now we say root arrow right equals temp. So this gets put down like that. And I have a typo here. These should all be root. Bad. Okay, so this is done. We're going to return root. So this is the return value from our call to insert. We go back to frame 3, and we said temp equals insert, so now temp is equal to this. So we have finished this call to insert. Now we say root arrow left equals temp. So root arrow left, which was this, is now going to be this. It's a 45 with a 47. And then we return root. So this is a return value from this call to insert. We come back here. We were saying temp equals insert. So now temp is this return value, which is a 50, a 45, a 47, and a 60. And what does the code say? Root arrow right equals temp. Well, here's our root, so root arrow right should be replaced with all of this. So it's a 50, a 45, a 47, and a 60. And then we return root. So all of this is the return value. So back here on page 1, we were saying temp equals insert, so temp is equal to the following. And then we said root arrow right equals temp. Well, this is root, so all of this should be replaced with all of this, right, which makes it look like this. And then we return root. And so this is what we return from this one call to insert. And so now root looks like the following. And it's our original tree with a 47 inserted into it. So that one's not so bad recursively. You go straight down a bunch of times and then you come back up a bunch of times. right? We're kind of following a direct path to the insert point, whereas traversal farms out. So we keep going down and coming back up. Okay, but you want to be able to replicate this in your heads or on paper, right? Because this is what's happening when we make these calls. And to work with it on a practical basis, right, we just want to think this is inserting this into this subtree. And this is replacing the right subtree with this new subtree. But it's still useful to be able to at least once or twice go through the lowest level of this and actually follow how these call frames are working. And the only reason the recursion is working like this is because, you know, in this instance in call frame 3, we had a variable temp, we had a variable root, but those were different from the call frames that we had in call frame 2, where this was temp and this was root, right? They're local variables. All right, did that make some sense? All right, so that's the magic of recursion. So questions on that? Is that a book bag? A pen bag? Yeah, oh, that's awesome. All right, so what I want to talk about tomorrow, I want to talk about deletion, because deletion of a node is a special case. It takes a few operations, but I want to talk about deletion, and then I want to look at some other applications of trees. So we'll look at doing some stack-based calculations and things like that. And any questions you have on ODPs, PA3, any of the stuff we've done, or the midterm, bring them tomorrow to class. Okay, otherwise we'll just keep going with trees, and then we'll start talking about balancing trees. All right, I will see you tomorrow.